Okay, welcome to today's lecture. Can you tell me regarding the noise level? Is it okay? Should it be louder? Louder? Okay. Like this? Okay. You give me signals. Okay. Today is going to be a big week. We will introduce the Black-Scholes model finally. So this is a very, very important week. But before we go ahead, I just want to say two organizational things. Firstly, there will not be a problem set this week. You will have 1 week to do whatever you want, go over the material or relax or whatever. So next week we will discuss implementations, numerical aspects of the Black-Scholes framework, and then I will hand out the problem sheet where again it will be a coding sheet. This is one thing. Secondly, probably I said this already, but the midterm, like my plan for the midterm is to have it after the recess week. And the format that I would like to have it is an online questionnaire that you can fill in within a week or so at your time of your convenience. So that way, even if you travel a bit longer or the midterm doesn't impose any restrictions. But since I'm new here, since this semester, I don't know yet how things work here perfectly. So I'm going to figure that out until as soon as I can, and then I will confirm. But that would be my plan. Okay, so let's start. So this is the agenda for today. We will derive actually this Black-Scholes model, the Black-Scholes formula, the Black-Scholes partial differential equations, which is a model for pricing of derivatives in a log normal market that we've already introduced the previous two lectures actually. And to give you, I'm pretty sure all of you know, or if you've heard of Black-Scholes framework. Despite, let me just tell you, this is a tremendously influential and important step in quantitative finance. Like this formula or this framework was rigorously established somewhere in the 70s. I don't remember exactly, but roughly in that area by, Black-Scholes, and those were two economists, and actually Merton, who was a mathematician, who made it the mathematical framework rigorous. And it's so crucial because this is really the first step to consistently use mathematical theories in the context of option pricing, which is precisely why you all are here. So this is a really influential, big leap in this QF theory. And yeah, without it, financial markets would certainly not be the size that they're now. One funny comment you might know, might not know. I didn't know it for a long time. So actually, it was not Black and Scholes who figured this formula out, but it was slightly earlier a mathematician named Ed Thorne in California. I don't remember which university in particular, but also in the 70s, he discovered this framework. He actually he was really into gambling, and he wrote a book. It's called Beat the Dealer. And during this process, he discovered that these principles should be true. And what he did is he started a hedge fund instead of publishing this formula. And I think I read that consistently for over 30 years, he has made on average 20% returns. So he has become incredibly rich, and his hedge fund is doing tremendously well. But he didn't get the Nobel Prize, in contrast to Black-Scholes and Merton, who academically published it. But yeah, it depends on what you like. Okay, so then next week we will discuss. So yeah, today will actually be we will derive the PD. We will discuss the economics behind also the shortcomings or potential shortcomings of this framework. And next week we will discuss methods how to solve the resulting equations. Now, who has or who is familiar at least slightly with partial differential equations, so PDEs. So I will abbreviate it. Okay, 1, 2, 5%, 6%. Okay, should I briefly? So I think today is really important, and the next lectures next week and the week after that will also be, I think, easier. Today, unfortunately, it will be like many things will come together. So what I would do maybe is just give you like a simple start to this lecture, recall what a PD is, what the difference to an OD is. So for those of you who haven't heard it at all, just to clarify the notation and then stuff. How do I do that? Here. Okay. Mm-hmm. Interesting. Has anyone experience with this machine? So, has an idea why the pen is not working or how to fix it? Okay. Has anyone experienced with Windows? Maybe that's... Sorry, say that again. Empty paint? Yeah. Nothing. Do you okay. Okay. So either I can call okay, 7. No, it's already past your time. So maybe I write on the blackboard, and hopefully, like that will be. Mm-hmm. Okay. Does anyone see any pens? Okay, we're not off to the best start, it seems. No, but I need to write something, otherwise this lecture will be a bit dry. Okay, how about I run up my office? I'll be back in 3 minutes and with at least markers, and maybe I restart this device as well. Maybe it will just work afterwards. Restart. Okay. Okay, so everything, we have pens and this thing started to work again, so whatever happens, we're ready. So yeah, the plan was to tell you the difference or to explain to you what a PDE is, okay? And so remember, so far we have essentially seen ordinary or stochastic, but ordinary differential equations. So here you have a function f, say from r plus, so this is just the positive real line, to r or rd, whatever. And an ODE is something like a function, a relation between the derivative and f, maybe t as well, dt. Sorry, no dt. Yeah? Okay, what a partial differential equation is a function that depends not only on time but also on a state variable. So you have f, which goes from r plus and rd, say, to r, to the real numbers. Okay. And again, you have a relationship between the derivative and the function itself, but also the derivatives in the space, so in x. So for instance, what actually we will consider later on as well is the heat equation, which takes the following form. So you have partial derivative in t, f of tx is 1/2, that's just a normalization, but second derivative in space, f of dx. So partial because it includes partial derivatives in various its input. And I mean the difference between these equations is, well, the first one we have seen, essentially that's, for instance, if you take alpha to be linear in f, that's just like a population growth modeling. Whereas here what you can think of as an example is the evolution of heat in any medium. So RD is in the simplest case. So D equals 1, you have just a rod. Yeah? And you consider the evolution of heat. So if T is, for instance, 0, yeah? And I'll show you two scenarios. You want to see how heat evolves until a small time T larger than 0. Then what this equation tells you, well, it evolves according to the local curvature around T. So if you have x here, and you have consider a neighborhood of x, and say x has 11 degrees, can you read it? No. 11 degrees, and this here has 10 degrees. That means like the function here is relatively flat. And then, if you consider it at time 1, well, the new state, or time larger than 0, the new state will maybe not have 10 and 11 as values, but 10.3 and 10.7 and 10.3. I don't know, I'm making these numbers up, but like not a major change. However, if the curvature is very large, like if at x, at a different x, you have 100 degrees, whereas here you only have 10, then also the change will be much larger, no? Like, I don't know, 50 and 20, or I don't know, just numbers. Okay. So those are PDEs. And we will come back to them later in the lecture, so boundary conditions for PDEs and so forth. But actually this heat equation here will again pop up in the context of this Black-Scholes framework. Now, we're slightly behind schedule, but what I could do is I could give you a brief idea of the core of this whole story in a simplified setting, And then we will go through all the details in the actual setting, more realistic Black-Scholes setting. But then you've seen it twice, once for a simple, not really realistic model, and once for the Black-Scholes model. But then you see the idea twice. So I think this is a good idea here in this context. So let me do that. So what is our goal? What is the goal in Black-Scholes framework? It's the same as always. We want to compute prices of options, and we also want to compute replicating strategies. Okay? And here, we have seen this in the in the last week. Okay, so this was the binomial model. You have a stock S, a bond B. Stock can take only two states. Either it jumps up, it jumps down. Bond is deterministic, has a deterministic growth, here 5% in each period. And you have, in this case, call option V, which outputs stock minus strike price in each scenario. And what you wanted to do, or what we set out to do, is calculate the value at time 0, the price of this option V. And the way we did it is, as always in this course, by replication. Yeah? Replication means the following. I find a portfolio, so here delta units in stock, phi units in cash, which perfectly replicate at the terminal time the outcome of the payoff of the option. Yeah? And if that is possible, it's a big if, but if that is possible, the price of the portfolio today has to be the price of the option, otherwise there's arbitrage. That's the whole course so far in a nutshell. I mean, not the mathematical part, but the econ part. Now, this is a model in one period, two nodes. I said if, and really it's a big if such a portfolio exists for which you can perfectly replicate your option, then it's the price. But why should such a portfolio exist in general? C, this function, or V here, it's called V here, could be anything. Yeah? Here, magically, because I have two nodes, two unknowns, and two equations, I can do it. Yeah? This was just here. I have two unknowns, or two parameters I can choose, delta and phi. Two equations, no problem. However, whatever this V function is. But what if I had three equations here? In general, it would not be possible. So what it means is I want to replicate any function with a linear function, essentially. That's not going to work. Yeah? So why does it still work in a multi-period and continuous time version of this, where, like, I mean, intuitively the density of Black-Scholes is a log normal density, so it can take infinitely many values, not three, but infinitely many. So how does it come that all of this still turns out to work as well in continuous time? That's what I'm gonna show you. And again, this here is not the Black-Scholes framework. This is just a very heuristic, simple, explanation that you can go over. If it helps you, fine. If it doesn't, you will see everything in the lecture notes in full generality. Yeah? But essentially what we have is, so in this one period model, we can rewrite this. And I'm going to assume here that BT is just 1 for all t. To make my life simpler, again, this is just for the first 10 minutes of, next 10 minutes. Yeah, no interest rates. Okay, so what we had is essentially delta times S1, or let's call it delta 0. I decide today, so 0. Plus delta 1 plus phi, that's the unit of cash. Well, B1, which is 1, has to be the value of my option, and I call that option C at time 1. Yeah? C is the call option, say. Any option, but call option. So, and then we had the price has to be delta 0 S1 plus phi. Delta is S0 plus phi 0. Value of the portfolio today. So what I can do, just a trivial algebraic reformulation, I can also write this as delta 0 times S1 minus S0 plus phi tilde 0 is equal to C of S1, where, well, phi 0 is precisely this number, phi 0 tilde. That's just adding and subtracting a 0. Yeah? So what I've gained by this is just the convenience, that's gonna be clear in a minute, is, so the interpretation here is the following now. Phi 0 tilde is the price or the amount of money I need to have today, for which if I just make bets on the market, on the increments, yeah, I will be able to replicate the stock. Not stock, the option, the payoff of the option at the terminal time. Yeah? I mean, that's just an algebraic trivial reformulation. Now, how would that look in multi-period times? Okay, let's put phi tilde 0 at front plus sum t delta t st plus 1 minus st has to be s the payoff at terminal time. That will be the multi-period framework. Yeah? At each time you make a bet. And the continuous time, so the continuous time limit, we have seen continuous time limit would then be the following: integral of 0 to t delta t ds t is equal to C of st. That's just the definition of the stochastic integral. So that means the interpretation is here again the following. So I have today, I need to set aside money phi 0 tilde. I make bets in the market. I re-evaluate those bets all the time, and eventually I'm going to replicate my payoff. Now, so this is what we start. Why does such a delta exist? Yeah? And from here on, I'm making my life again simple. S is just a Brownian motion. No exponential growth, just Brownian motion, no interests, no drift. Volatility is 1. All these parameters will be general in what follows. Here is just to get the basic idea. Why does such a portfolio, a strategy delta exists? And why did I tell you something about PDEs just, 20 minutes ago or so? So it turns out, and this is like really fundamental, that that you can use PDE theory to calculate this delta. Yeah? And I'm going to write first the condition, and then we're going to check. Yeah? So suppose there exists, there exists is a function phi tx. Yeah? So it depends on both time and space, such that the following two condition holds. Phi of terminal time at maturity is just C of x for all x, and the derivative in time plus 1/2 the second derivative in space is 0 for all t in x. So suppose that we have access to this PDE. So we have access to a solution to this partial differential equation. Yeah. If we have that, then what can we do? We apply Ito's formula. Ito's formula will tell us that C of ST is, by the first condition of the PDE, by the boundary condition, is phi of S at T ST. That's the boundary condition. Yeah. So now Ito's formula tells us that's phi of 0 S0, that's the number, plus delta X phi of T ST dSt, that's the stochastic term, the Ito term, plus delta T phi, let's put it in one line, plus 1/2 the correction term. So this is really just application of Ito's formula, nothing more. So let's call this 1, this 2. So this is 1. This is 0 by 2. Okay, so all of this cancels. Hence, you see what delta is. So this is delta. Delta T ST. Yeah. So it is really Ito's formula that makes the connection between solving partial differential equations, so finding solutions, functions phi which satisfy these two conditions, and calculating the price of options, because that's going to be this number. That's just a number. S0 today is known. That's a number. Well, and why you would do that, of course, is because you have a lot of theory for partial differential equations. Those appear naturally in all sorts of areas, physics in particular. So people in physics have studied them for ages, and now in finance you can apply them. So that's the reason why, or one of the main reasons why you would like to have this correspondence between solutions to PDEs, option pricing, and hedging. Yeah? Because this also, by the way, this is also very important. This doesn't only tell you the price of the option, but it tells you the replicating strategy. Yeah? So if you want to achieve the replication, how should you trade? Well, exactly according to this. Okay. Okay, let's go back. Let's go back to the lecture notes. So this is the agenda today. We derive all of this in the Black-Scholes framework, which is a much more realistic framework for, stocks. We derive it more rigorously. We discuss boundary conditions, and the second part comes next week. So I think I've said all of that essentially already. It's a mathematical framework that's based on economic reasons. That is, as always, nor arbitrage and replication for this course. Ito's formula is the essentially main tool here. Yeah. Good. So this is now really the Black-Scholes model precisely the one they considered in their paper. That's precisely the model. We have log normal dynamics. So those we have seen are, it's an exponential growth model for a stock. So a lot of stocks follow this sort of dynamic. Equities, and it has a noise infusion, so there is volatility or noise is the sigma. And we have access to a bank account, which is continuously compounded. The returns here are constant, deterministic. If you want, one very easy generalization of this model is you could take, let me do this one. Could take R to be a function of time. That's just that the interest is not constant, but it varies in time, but deterministic. So then you would just have bt is b0 times exponential of the integral 0 to t rs ds. Nothing changes really. All the math goes through precisely as it will go here. It's just uglier to write down for obvious reasons. So later on, if you want to recap this model, you can do this as an exercise. But more importantly than this assumption is the restriction that there's no restriction on short selling. So short selling, I will discuss this in 1 or 2 slides, is somewhat, not as intuitive as going long on an asset, where you believe that this asset is valuable and you buy it, but instead you short it, you borrow it. So that's certainly an assumption. Then there's no liquidity restrictions, meaning that whenever I want to sell something, I will find a seller who is, I want to buy something, I will find a seller who's going to sell me precisely this amount of stock that I want for precisely the amount that Black-Scholes suggests. We will discuss this later on as well. That's also clearly not a super realistic assumption. No transaction costs. So I can trade for free, which again, is not realistic. We'll also ignore dividends. And the thing that I want to mention here, so these are assumptions, some of them more unnatural, some of them less unnatural. What we're going to do today, using those assumptions, we're going to derive these formulas. More sophisticated models, like you can always, for instance, inject transaction costs. I have a bid-ask spread. But then the formulas get messier, the theory gets less clear. So today we're going to start, or I think throughout this whole course, maybe at the very end, I don't remember. But essentially we're going to understand things in these simplified models. It's crucial for you to understand that this is really only a model and not accurate reality, but as it turns out, and you can analyze this, it's sort of second order effects. Meaning that, okay, if you have transaction costs, the outcomes will change by a bit, but not fundamentally. Prices are not going to jump from 0 to 100 or anything like that. It's small effects. Depending on how much transaction costs you assume and so forth. Okay, so short selling. Short selling. So first, long is again relatively clear. You borrow money from the bank, you buy some asset. If the price goes up, you're happy with yourself. You made the right call, getting the right stock to invest in. However, you have also a mitigating effect, namely that there are interest rates. So if there are 5% interest rates and your stock went up 4%, effectively you lost money. You should have just put it in the bank account. You would have gained more. Yeah. On the contrast, like if price goes down, then you're losing twice on the interest and on the stock. No, but still, this is very intuitive. Shorting is less intuitive and less natural if you think about it. So this exactly mirrors what a long does. What did I want to say? Okay, yeah, if the price goes up, you lose twice. If the price goes down, there's this effect of the interests. And it's also not so, I mean, you can buy you can short assets on repo markets, but still there's more modeling implications involved with shorting that I just want to briefly discuss. Yeah? And so for instance, let's make an example. You own IBM shares, any shares, let's call it IBM. I want to borrow them. Would you borrow them to me? No, yeah, thanks. Exactly, yeah, you shouldn't borrow them to me. I mean, for obvious reasons, like, I mean, there's some admin costs somehow. You should get some reward for this. But crucially also, there are margins. So what happens if I run off with the money? There's a risk for you involved, right? So what typically would have is I would have a government bond. I would put it as collateral. And then you say, okay, if I run off, nevertheless, you get the government bond. So say that IBM today is valued at 100. I would need to put up government bonds valued at 100 for you as well. That should sound fair. Now, however, what happens if the price of IBM increases to 105, say 110, whatever? Then probably you would not be like super satisfied with the government bond that's still valued at 100. Yeah? Because now I could run off and still make profit. So what you would do is I would need those sort of variation margins. So I would need to put up some more cash, some more collateral. And if I don't have that, then, well, what do I do? So these things can have like snowball effects. So that would be essentially called a short squeeze. So for instance, precisely what happened to GameStop. Yeah. Yeah, you heard of this. All perfect. Okay, yeah. So that's shorting has other implications as well. That's just what I want to say. So it's certainly an assumption that there are no restrictions whatsoever on short selling, and all these things we ignore, of course. Okay, that's short selling. Liquidity. Now here maybe what. The assumption was that there's always a person, Black-Scholes model will tell you the price is 100. Yeah? And the assumption is that I want to buy it for 100, I will find someone to sell it for me to 100. If you think about, for instance, commodities, if you think about oil, so that's probably not super reasonable. Yeah? Maybe I want to buy it for 99, maybe someone wants to sell it, but only for a 101. Is the trade going to happen? Is no trade going to happen? Eventually, what turns out like markets are just negotiations, so some trades will happen actually, yeah, and not precisely at the price that Black-Scholes suggests. So all of these will have an influence, yeah. And what we're going to do, this is actually the next slide. So if we have a difference in prices from buyers and from sellers, we're going to ignore this bid-ask spread and just like see this money as slippage. So it will just disappear from the market. Yeah? Again, important. There are many models and many papers and many like chapters of books and whatnot that deal with these kind of things, but it's second-order effects. Yeah? Though interesting, okay, I just remembered like a funny anecdote in that context. So I was visiting earlier this year a researcher in Stanford, and he worked part-time at Amazon, and they hired him precisely because of these second-order effects. And he told me, he told me what he was doing, like not in this context, but general in optimization. And I was wondering because like all these effects seemed so tiny. And then he told me, well, you need to multiply by the revenue of Amazon. So 0.01% of a huge number is still a huge number. Enough for them to pay him to sort these things out. Yeah. So yeah, but okay, in this course, again, we will do the basics, the fundaments. Later on, you're more than welcome to read up on all these refinements. Okay. Let's keep going. I think maybe we need 20, 30 minutes, but since we had essentially a break, let's keep going. So all of these were discussions on the assumptions. Now let's derive the model. Okay. Now comes the math and econ part. So this is just the repetition. So all of what we're going to do is based on replication. Replication meaning in portfolio that perfectly cancels or replicates the payoff of our whatever option we have. If we have replication, then there's no arbitrage. And so what we need to do is create a portfolio that will eventually, like a terminal at maturity, precisely yield the payoff of the option. Now, this is again a priori absolutely not clear. I showcased you in this Brownian motion. We call it Brownian motion, right? Not Wiener process. I forgot. Okay, we write W. That's usually okay. In the Brownian setting, I explained to you roughly why this is true. And one important thing here is maybe to remember that this portfolio that we're going to construct, or also the one we've constructed, is dynamic, not static. So earlier in the lecture, in the very first lectures, or the very first lecture actually, you've seen how this can be used to calculate prices of very, very simple options. Like you have one currency, a different currency, you want in a year you need to have a forward contract from that currency. What do you do? Sell this one, buy this one, that's it. So those are static options, static portfolios where I decide today and then I'm going to stick with that decision. Here in these complicated stochastic models, there will essentially never be static portfolios. It will essentially always be dynamic portfolios. And we will see actually why this is the case. This will be very, very clear from the mathematics. Yes, so replication, cost of portfolios, cost of options, cost of portfolio at initial time. That's what we need to do. So let's do now the following. So V will actually be this, I'm going to already give you a look in the future. V will be the solution of this PDE, similar as before. It's called phi before, here it's called V. So V is just a function, the value at time t. We think of it like that. It depends on the stock price, on time, and crucially, like at the terminal time, maybe I should write that down as well. So V T S T is just our C of S T. Yeah. So at terminal time, the value of the payoff is just, well, the payoff. At terminal time. The question is, what's the value prior to the terminal time? And so this is our idea how we're going to do it. That's engineering, essentially, backward engineering. So we're going to call this here, we're going to call this here minus CT. So the value of the portfolio at time t, and that's the value of the replicating portfolio, if we have one. And what we're going to assume, now that's really crucial, is not only that at terminal time they coincide, but we're going to assume that they coincide for every time step, for every instance in time. So pi t should be 0 for all t. So this here holds for all t. So this will help us to pin down what this value function, what this delta is. Yeah? The reason it will help us is because now I have actually two conditions. One, that pi, this difference is 0. And second, if a function is 0, then also its derivative is 0. So I can take the differential of pi. So this is where stochastic analysis will come in. So those are really two conditions. So this is 0, this is condition 1, and this is condition 2. And I think, like actually, this condition 1, we will only use for this equality. So that we can actually, once we have delta, we can calculate phi, which was the amount of cash we're carrying. Yeah. Everything clear? So the next slide will contain all that is there to say, essentially. So is everything clear? Are there any questions? Again, if you have a question, probably you're not the only one. So I encourage you to please ask. Good. Okay, so pi t is 0, ct was the value of the replicating portfolio, v the value of the option at time t. We're now going to use the this fact, so that the evolution, the dynamics of pi is just also 0. Yeah. And that will be quite cool because we will do two things. One is mathematical, and one is purely econ reasoning. Yeah? And those two things combined will give us the solution, essentially. So the first thing we do is, sorry, okay, this is minus ct, right? And we know that d pi t, which is d of vt plus minus ct, has to be 0. This was written on the last slide. So we're going to do two things. First, remember, v is a function of time and the stock price. So the only, what we have seen, the way to calculate differentials is by using Ito's formula. That's the correct way. Yeah? And that's what we're going to do here. So that's really just, essentially this follows from this Taylor expansion, as we have seen. So first derivative in t, first derivative in the state, or in S, times 1/2 second derivative in this squared term. If I do the Taylor or approximation to a power of 2, that's the term that I'm seeing. Yeah. Good. There's one technical aspect here, yeah, that I want to share. So what we have done so far is Ito's formula for Brownian motion only. S is not a Brownian motion. S itself has a stochastic dynamics. So S is the solution of an SDE. And perfect. This is Ito's formula from last week 3. So this was Ito's formula for Brownian motion. Now what happens if we do if we want to do here ST an expansion of a function that depends on ST, where dST is alpha ST dt plus beta T ST dWt. Yeah, for instance, alpha linear in S is just the log normal model, alpha and beta linear in S. So that's precisely the one that we have in in the Black-Scholes framework. So how does the Ito formula change? Any ideas? So, okay, I see unhappy faces. So let's say I have this S, which follows those dynamics. S follows these dynamics I've written here. S is a solution to a SDE, stochastical differential equation, like the log normal model. How does Ito's formula look like if you want to expand a function f of t st? So you have a function now not written on Brownian motion, but on Ito diffusion, S. How does Ito's formula look like? And I'm going to write this down, but it's the very same proof as before. So maybe let me... Is it okay if I just write S wherever? So if I write S like this, is it clear what I mean by this? Okay, yeah. So we want to have the same thing. Yeah, that's gonna be, the first part's gonna be the same. And the only difference is that here I will have ds square, which is beta square u su du. And the proof is really precisely the same thing. Remember, the proof is based on I expand this function f, like in a small time step, linear term. In t, I get t plus 1 minus t, which is precisely ends up in this du integral. I do a linearization in x, so I'm getting an s increment. I do second order expansion. I get a ds square integral increment. Yeah. And if you consider this s, what does a ds square increment look like? Yeah. So that's just about, how's it called? A plus b square is a square plus AB plus B squared. So dt squared plus dt times dw plus dw squared. Let me maybe write this also down. So ds square is, alpha dt times alpha dt plus 2 alpha dt times beta dw plus beta dw beta dw. Just formally, but all of this makes you can make it perfectly reasonable, precisely. This write Ito's formula using integral approximation by telescopic sums. So this is dt squared. So this will disappear if you do have dt infinitesimal. This is small order dt because dw goes to 0. W was continuous, so wt plus epsilon minus wt will converge to 0 as epsilon goes 0. And this here is beta squared dt. If you're bored this week, since you don't have a problem sheet, you can try to make this a bit rigorous. Yeah? But really, there shouldn't be nothing new happening. It's precisely what we did before. Okay. I'm going to wait a minute to let you finish writing, for those of you writing, and then go back to the... No question? Okay. Okay, so back to Black-Scholes. What we've done so far is the first part of this slide. Ito's formula. And you've seen this is why I wanted to explain all of that in the beginning, just using Brownian motion. But we have now computed the dynamics of V, the value at time t. So remember, our condition was that the dynamics of V are equal, essentially, to the dynamics of C, so the value of the portfolio. How does the value of the portfolio change over time? I claim it's this one. Why is this the case? And again, that requires maybe this. I can write this on here. This requires a different reasoning. No, maybe let me write this somewhere else. Okay, so we had CT or minus CT. Minus CT? I don't remember if plus or minus. Probably minus. Delta T st plus phi t bt. Yeah? The value of the portfolio at time t. How does it change? And think about this. Forget, you can forget almost all mathematics. Think about this economically. Yeah? And think about a discretization. Don't think about continuous time, but think about you have a t and you have t plus dt, so a tiny the next second, or maybe better the next day. So how does the portfolio change between today and tomorrow? Okay. So what will happen? So say that today the portfolio value is delta t st plus phi t bt. Tomorrow I will be given the opportunity to rebalance my portfolio. Maybe I will buy more stocks and sell some cash. Maybe I will do the opposite. But how much cash do I have, or how much, do I have at my disposal to do that tomorrow, given that I've chosen delta t and phi t today? Suppose you have bought 1 unit of stock, no cash. Stock was at 100 today. Now it jumped up to 200. How much money do you have tomorrow? 200. Now you can rebalance. For those 200, you can buy one stock, half a stock, and the bond, or you can just buy cash. So tomorrow, and by tomorrow I mean this is, tomorrow is like t plus dt, of course. It's a discretization. Tomorrow, before rebalancing, I have delta t st plus dt plus phi t bt plus dt. Yeah? That's the money I have. And that I can rebalance. So now if you subtract tomorrow's and today's value, what you end up with is precisely this here. In window, perfect. It's precisely that. Yeah? And you see, interestingly, just two important comments. So if you would apply Ito's formula, which you could do a priori as well. We haven't written down Ito's formula for products of processes, but this is one stochastic process, and S is another stochastic process. So you can imagine that D of A, B, where A and B are stochastic processes, will follow an Ito formula as well, with cross terms. That's reasonable to expect, and that is really true as well. But if you would do that, it would be much, much, much more complicated, and you would need basically more complicated reasoning. So the true or the real reasoning here is really this purely economic reasoning to calculate the differential of the value of the portfolio. And that's called self-financing. Simply because, you rebalance your portfolio solely based on the amount you have at your disposal. There's no infusion of cash coming in somewhere. You're not throwing away money or putting it somewhere else. So this is a very, very important concept that you will see often, self-financing. And that's also, by the way, where precisely in the first slide, just to make the connection, that's precisely what we had, st plus 1 minus st. We didn't have any phi because dB is 0. In our example, B was just flat. So that makes the connection to our teaser in the beginning. Okay, let's have a 10-minute break or 12-minute break, and after the break, we will put things together quickly and obtain Ito's formula. But I think, yeah, it's very, very late. So see you at 25. Yeah. Yeah. Okay, welcome back. Now, so what we've maybe a recap what we've done so far. This is our model. We have a log normal SD. We have the money account, which just evolves exponentially, returns our R. And we've derived, so what we've done is we have the value of the payoff today. We've set up a portfolio called C, delta units in stock, phi units in cash. We set up a portfolio in a way that it cancels out perfectly, replicates perfectly the value of the payoff at every time. In particular, pi, this difference is 0. The derivative of pi is 0, naturally. And what we have obtained is, by using Ito's formula, the expansion or the differential of the price Vt. And what we've obtained using the concept of self-replication is the differential of the portfolio, the value of the portfolio. That's the story so far. Now, what is missing? So what we want to achieve is that the dynamics of V and the dynamics of the portfolio are the same. If they are the same, then they eventually will yield the same thing, right? So how do I, and now we have two parameters that we can freely choose. How do I choose these parameters? And I claim there's only one approach that could work. Yeah? And the reason is the following. So think about all these terms that appear here. So you have 5 terms in total. Yeah? BT, again, so BT is just, BT is B0 e to the RT, so dBT is BR dt. Right, that's the cash account. So you have 5 terms. 3 out of those are of the form dt. This we've actually also seen, that this term is a dt term. Yeah? So all these increments behave like dt, whereas this guy here, the ds and the ds term here, they behave much more irregularly. They are the random terms. They behave on a much rougher, in a much rougher way than dt. So intuitively, the only way that I can assure that the dynamics of V and C are equal is by ensuring that this random huge term behaves in the same way. That's the only way I have to achieve that those are equal. So that's called delta hedging. So what I will pick is precisely delta to be the term in front of the ds term. Yeah, let's go back. So remember, delta is minus the derivative of V. Delta is minus the derivative of V. So this here is this here, or minus this here, okay? So that when they're summed up, they cancel. And like intuitively, this is also, if you just heuristically forget the maths, if you think about this, it means that you try with your replicating portfolio to take as much randomness out of the evolution as possible. So this is really the truly random part, and those are the more deterministic parts, in a way. So what you do by hedging or just replicating is you try to make the claim, the payoff, less random. Yeah? So delta is precisely the term here. That's it. And this eliminates this, so to speak, random component. Okay, so we have chosen one parameter. Now what can we do? Okay, plug this into this formula. That's precisely so this was again Vt plus Ct. So dVt plus Ct. We have the expansion. The ds term, which appeared here twice, now cancels by the choice of delta. So I end up with this equation. Derivative in time, derivative in space, second derivative, plus phi t bt, dbt. And now I'm going to use the second of the two assumptions that I had, or prerequisites, that pi, not only d pi is 0, but pi is 0 as well. So that's, remember, this was, so this whole thing is delta. And maybe let me go back. So this equation that where I've written on something, it comes precisely out of this first condition on that pi is 0. That's exactly this one. So we've used now the two conditions that we have. I went in the wrong direction. Okay. That means, first of all, we can plug this expression for phi t in, because, like, I mean, phi t, so actually we had phi t dbt, but dbt is phi t rbt dt. That was just the evolution of the cash account, interest rates. So this is the first term. Second, we have seen in this E2 formula that the ds square term is a dt term multiplied by the volatility squared of S. That was the E2 formula, this version of E2's formula for E2 processes that I showed you. So that is the second term. And if we have done all of that, plug this expression in, we arrive at, finally, at the Black-Scholes equation. And this is really the Black-Scholes PDE that whenever you would open a textbook, you'll find this equation. Now, the way to use this equation is like reverse engineering eventually. So we have this equation, this partial differential equations, that the value process needs to satisfy. And what we're going to do is, well, we're going to use some theory for solutions of PDEs, numerical or just theory, get this solution, and then we have the price, that's just V at 0, and the hedging strategy. So remember delta. Delta was precisely the derivative of V. So the solution of the PDE tells us everything that we want to know, price and portfolio. But this is really, really cool. Yeah. in particular, this is very general. So remember, like I've often written C to indicate like you can think of a call, but by no means that's necessary. Like this is true for every call, for every whatever option, that structure of a payoff that you're interested in, depending on terminal time. Now a question for all of you. If that is true for every payoff, I have this equation. Should that mean that every payoff has the same price and same hedging strategy? Clearly no, but where do we see it? In the boundary conditions. So this is a parabolic PDE, second order. And as is with the case with ordinary differential equations, you need some conditions to make the solution unique. Yeah? Here it will be like significantly more complex than for ODEs, as you will see. But still, this philosophy is the same. Like you have an equation that describes you an evolution, but the boundary or data or whatever, those conditions are called differently in different fields. But those conditions will select a specific solution, the solution that you're interested in. And what turns out here is it here, second order? You actually need 3 boundary conditions. And I will explain that. Now. And yeah, we will also see that this equation that we've derived, the Black-Scholes equation, is essentially the heat equation in disguise. Yeah? If we do a clever trick, we end up with the heat equation. But okay, so again, very basic. You have an ordinary differential equation, or just an integral equation. Y is given, the derivative of y is given by x squared. What is the solution? Y is 1 over 3x to the 3 plus a constant. Any constant. Any constant will be a solution to this equation. If you differentiate, it falls out. So what you need is to fix the value of y at least one choice of x. If you do that, you select a unique solution. Now, the same thing happens to partial, or actually, okay, second order ODE. So if you have something that depends on a second derivative, in principle, you need 2 to specify the value at 2 conditions. Yeah, so these would be called boundary conditions here. And this same principle extends. So if you have order 3, then typically you need 3 conditions. If you have 10, you need 10 conditions. That's for ODEs. So for partial differential equations, it's the same story. Yeah, here for us, remember, we had 1 derivative in time and 2 derivatives in space. So in total, it's an order 3 differential equation. So what we need is 3 boundary conditions to pick a specific solution. And the first one is trivial. The first condition, that's the terminal condition, right? The value at time t is just whatever payoff we have at time t. F is given. F is a call option, for instance. That's your input into the system. I want to price a call option. So F is just S minus K plus, whatever. That's your input. So this first, or put whatever, I mean, any option. That's your input. So this is that's trivially a condition. Now what is a priori bizarre is that you need to specify some other conditions as well. Yeah. Okay, why is that bizarre? So this here is the natural condition. The value of the portfolio at the terminal time has to be the same as the payout of my option. And actually, if you think about it, this is the only condition in our derivation that we have used. Yeah? We have not used any other conditions on the solutions. So either I've cheated. Well, actually, I have cheated. So what happens is that, remember that in all of these Ito formulas that I explained, there was always this condition if f is nice. Yeah? You can define the stochastic integral for nice functions. You can differentiate nice functions. Nice functions means like differentiable with reasonable growth and so forth. This PDE will have many, many solutions, many of which are not nice. So you can think of it as follows. But the other conditions, the other boundary conditions, restrict yourself to a nice solution. And we will see that. But that's just, I have to say it to make it mathematically correct. That's the reason why we need all those boundary conditions. Yeah? To choose the regular solution of the PDE. That's how you can think about it. Okay, so let's start by considering what those boundary conditions are and where we get them from. Because a priori we only have, this is the only input that we have, F. And we've already used it in the terminal condition. Okay, so there are one type of boundary conditions for these type of PDEs, is Dirichlet conditions. And if you have a call option, then what I'm claiming is that, let's consider first the first equality. Yeah. So this here is an a priori assumption we put on the solution. Yeah? And now comes not mathematical, but economical reasoning in some sense. So V is the value, this here is the value at time t if my stock price is at S. And remember, S had log normal dynamics, so it was always positive. It models like a normal stock price. So what happens, and that's a call option, what happens if the stock price is extremely small? To make it concrete, yeah? Because like this is one of the things that you will actually need to do. So you will actually need to come up with these boundary conditions if you implement it later on in your life, I assume. Vf of x is x minus k plus, and say k is 100. So what is the value of this option at time t if I know that my stock price is at 90? Not so clear. You don't know precise the value. What happens if the stock price is at 1? And very, very small, right? So if today is 1 and say it expires the option in a couple of days, I'm not going to bet a lot of money that the stock price all of a sudden reaches from 1 to 100. What happens if the stock price is 1 cent? It's really going to be 0. Yeah? So this here is, that's this condition. Yeah? Similarly, okay, this is poorly written. Similarly, what I mean here, S behaves like this for large S. So again, same call option. Strike price is 100. Now the stock is not at $1, but at $200. Day to expiry is a couple of days, or a year, whatever. I'm not going to believe that it jumps down all the way to below 100. If it's $1 million, the stock price, it's even less likely. So if for astronomical S, essentially I'm linear in S. Yeah? That's what I mean here. I have linear growth, the slope is 1. Those are my 2 boundary conditions. The function at the boundaries, and boundaries here are essentially 0 and infinity, because we have the exponential, so the solution lives on 0, infinity. I specify those functions in T. One is 0, one has linear growth. And you can, I mean, here it maybe is a bit apparent what I meant before. These boundary conditions restrict yourself to regular solutions. That's a solution with linear growth. Yeah. For these type of linear growth functions, you can use Ito's formula. If you wouldn't have this restriction, maybe your solution would oscillate crazy, still satisfy the PDE, but oscillate like crazy. Ito's formula would not be applicable. It's too irregular. Yeah. Okay, same story. Another type of conditions is Neumann boundary conditions. Those are not on the asymptotic behavior, but on the asymptotic slope of this value function. And again, let's do this calculation. Call option f of x is x minus k plus k is 100. Anyone wants to explain why the value at any time t, or the marginal value at any time t, if the stock price is extremely low, is 0? It's the same type of explanation as in the last slide. Exactly. So essentially, you don't get paid out in any state. So if S is very small, so it's 0, the slope of 0 is 0. Same reasoning here, of course. Like if S is very large, you get paid out anyway. The call activates. You get S minus K. The slope of that function is 1. Good. So this is important for you to understand because when you're going to be implementing this Black-Scholes framework, it's actually the algorithm is relatively simple. It's really closely related to the one you're, have implemented or going to implement in the last week's problem set in the binomial model. Yeah? It's a very similar algorithm, but what you need to specify every time is those boundary conditions. Yeah? And of course, like when you implement it, you will not specify this function to infinity and so forth. You will discretize. Yeah. Like if you have volatility, I don't know, of order 1 or 5 or whatever, and your stock is at 100, you don't need to go beyond 500. We've seen these light tails of the normal distribution. So that's events that are not going to happen. So you restrict yourself to some discretization, but in principle, what you're going to do is that. What is an appropriate for digital call option? Should I do it, or would you rather try for yourself? It's exactly the same reasoning. So digital call option is just the jumps at some strike. Maybe try for yourself. If you find this troublesome, ask me after the lecture next week, whenever. Yeah? Okay. Now the next 3 slides, I'm going to relate this PDE to the heat equation. I mean, this is really not necessary. You can also zone out for 5 minutes. It's just very important to state it. But I'm also not gonna do it very rigorously. It's just to give you the basic idea. The one important thing, though, is the bizarre thing about our equation is that it specifies terminal values. And typically, like from ordinary differential equations and partial differential equations, you would rather expect initial conditions. Like, I know the state of the world today, and it will evolve like this and that, how it's going to look like in a year. We know how it should look in a year and want to infer something back. So there's a trivial time change argument. If you have a solution to this equation, you plug in for tau, you plug in t minus t, it runs backward. You transform this forward, the terminal condition into an initial condition. There's no magic. The reason why this could be interesting, just to clarify why you should at least remember that there's something like that, is because obviously there's a lot of PDE solvers, and these solvers are typically for forward standard PDEs. That's the only reason. Okay, so forward, backward, it doesn't matter. It's just a matter of convention, essentially. However, I think this is like this. It should be like this. However, what you can do is, and again, this you can verify if you want. It's not essential. But what you can do is do a change of variables. Yeah. So V you can write, V you can write in terms of these coordinates, like V tau on x, and then derive the PDE for small v, or nu. That's probably a nu. That's just like standard calculus. You differentiate this function with respect to x, you differentiate this function with respect to tau, see what you get. And if you do, those are these formals. If you do that and normalize carefully, what you get is that actually this u function, or the u function, satisfy the standard heat equation. Yeah. So our value function is a reparameterization of the heat equation and vice versa. And why that is interesting is, well, because there's lots of theory for heat equation. That's just the standard second order parabolic PDE. Yeah? So this is really the thing that you could remember. Change of time gives forward, backward, and the clever reparameterization that you do not need to remember for any exam or anything, it gives you standard heat equation. Good. Now let's well, finish this lecture. I mean, no, almost. With two extensions. Firstly, dividend-paying stocks. So far, one assumption in our framework was that no dividends are paid out. So what happens if we modify it? And just to recall what we've discussed already in the last, probably in the last lecture, is that if a stock pays dividends, typically a small proportion of the stock, then and you're an investor, like to make this problem interesting, like you're not going to cash in on the dividends, but you're going to reinvest. Otherwise, the problem is sort of trivializes. But if you're an investor, really truly invested, then actually you care about the wealth process, which simply means like the stock price pays dividends. Immediately it has to jump down. We've discussed this because of arbitrage reasons. So it jumps down precisely by the dividends. But what you're going to do is you're going to use these dividends that are paid and invest them into the stock immediately. So S bar is your wealth process. Now, however, an option will depend on S, not the wealth process. So this is a slight modification. Here again, okay, the dynamics of S are these log, normal dynamics. A bank account, cash account, again, evolves just exponentially with rate R. D, the dividends, small proportion of S. And if you reinvest immediately, then that's the dynamics of your wealth process. I think we have derived that equation, I'm not sure. Yeah? Okay. Cool. So this is your process S. Okay, how does Black-Scholes function in this framework? Well, precisely the same way, the same principles apply as in the classical previous setup without dividends. So I set up a portfolio pi. Crucially, now it's written on S bar, not S. I have a cash, numbers in cash, phi, d delta, okay. And you apply the same principles. Pi should be 0, d pi should be 0. You get this equation. I mean, this time I just collected in one equation. Yeah. So this is precisely the equation that you get. That's Ito's formula. Maybe let me write this down. So this is Ito's formula. This was the S bar T. So this is the self-financing bit. Really, this is plug and play from what we've done previously. Yeah? Now, the only difference occurs now. Yeah? Previously, what we have done is we've said, yeah? Maybe let me write this down in color. So this here was DST, and previously here we also had DST. Right now we have DST bar. That is the random term. Previously, we had S here and S here, so we said delta has to be minus this guy, minus the derivative of V. Now, what you're going to do here is, however, the same thing. So remember, my argument why delta needs to be the derivative of V was because we need to kill the randomness. The randomness was ST. Here, I just expand ST and see which component is the random component. Yeah? I have a deterministic growth and I have the random component. Same story here. I have a deterministic growth plus the random component. So what I need is that the random component cancels. This is precisely what is written here. That was the idea, the first idea in classical Black-Scholes. Yeah. Cancel the random component. Previously it was S. We could simplify. Here it is W. Yeah. I need to be a bit more careful which part of S are really random. Well, and finally, you can write S as such, so you can transform S and S bar, and that's going to give you the solution. Did I write the solution? I didn't. Okay. Okay, so I understand, or I believe that I understand that today's session was certainly deep. We have connected various things. We have discovered the connection between pricing, stochastic processes, PDEs, continuous time hedging. So there was really a lot of things happening, and it's probably also, like, okay, I don't get so much feedback here, but I'm pretty sure that it's quite hard if you see this for the first time. Yeah? So don't be discouraged if today was intense. If you felt comfortable with today's lecture, you can try to make this rigorous. I mean, everything is here, just fill out the details. If you've understood this here, the dividends, then you've really understood everything today. So you're more than welcome to try that. What I would do now is, again, 2 case studies for barrier options that would be concerned with the boundary conditions and yeah, that would be it. Maybe one interesting comment still before we go to these examples. So this is direction of time. This is the PDE. Yeah, this is the Black-Scholes PDE. So what does this PDE tell us? In particular, it tells us what the price of a payoff is at maturity. V0, if we solve this for V, the function V, and we compute V at time 0, that's going to be the price. Now remember, our model was the following. I have a bank account which evolves exponentially. Interests are R, just a number, 4%, whatever. I had an exponential stock, log normal stock, evolving with volatility sigma, but also average returns of mu. So mu are the average returns of the stock. Mu could be 4%, mu could be 100%. I mean, not in practice, but in principle, yeah? Theoretically. So what the Black-Scholes formula tells us, mu doesn't appear here. It really doesn't matter what the expected returns are, because we're interested in replication. So we can factor, I mean, it tells you that we can actually factor out these average returns by investing in the stock. I mean, this is, like, to me, the first time I saw this was somehow a surprise. I mean, it sort of makes sense if you think about it for a minute. What does it mean? I mean, just because mu is high, you can buy the stock today at the same price. So if mu is high, then nothing essentially changes. But nevertheless, like on a first encounter, this is very surprising, I find. Yeah? And that's what comes out rigorously as a bonus of this theory. Yeah? Okay, now the finish line of today's lecture, just the examples. We're pricing an up and out call. So what does it mean? V at terminal time, it will look as follows. So that's as T. I have a strike. I have B. I have a barrier. And then it jumps down again. So it activates if the stock exceeds the strike. But then again, if it exceeds it by way too much, I again get nothing. So you can try to compute the boundary conditions, Neumann, Dirichlet, whatever you want for these options. Yeah. And I know this is simple, but at the same time, it's really important. So let's do that. Again, the principle is the same. Suppose that the strike price is 100, whatever number you like. Stock price is very, very small. The chances of it exceeding, like activate, that the option activates are very low. So the value at any time, if stock is infinitesimally small, should be 0. Same for the slope, for instance. You can also do if S is infinity, the same, you will actually have the same numbers. The option will not activate. Up and in call. So how does this look? I have K here, I have a barrier. Here nothing happens, and here it jumps up. So it only activates if the stock exceeds B, and then you get already paid the difference to K. What are the conditions? It's the same situation. If S is really, really small, the chances of it activating will be very small. Yeah. So really just to get these numbers, really forget about the math. Think about how much you would pay for this option if it follows this log normal SDE, if you believe in that. That's it for today. I will stay here a bit if you have questions. Otherwise, enjoy your evening and see you next time for the numerics of these PDEs.